Hello everyone, welcome to solve this math Olympiad algebra problem, and here we have 1 to the power of n equals to minus 4, and we solve this problem for the values of n. So here we first take the natural log on both of the sides. So when you take this natural log, and it is written as log of 1 to the power of n equals to log of minus 4. And now in the next step here we use the nice property of log, and we move this exponent n in the front of this log, and it is written as n times of log 1 is equals to log of minus 4. And now in the next step we move this log 1 to the right hand side, and it is written as n equals to log of minus 4 is divided by log of 1. And here we know that the value of log 1 is equals to 0, and here we know that something over 0 is equals to infinity, and it means that this expression cannot gives us the real root. So here we just write that it has no real root. So if it has no real roots, it means that this expression gives us the complex roots. Okay, so we write it here, it has complex root. So if it has complex roots, now we just take some working to find those complex roots. Okay, so that here in order to find the complex values of n, we just need to use the Euler's identity here. Okay, so you know about the Euler's identity. It is stated as e to the power of iota theta equals to cos of theta plus iota sine of theta. So here we check the behavior of this Euler's identity for the value of theta equals to 0. So that when we take theta equals to 0, our above equation is written as e to the power of iota 0 equals to cos of 0 plus iota sine of 0. And here we know that the value of cos of 0 is equals to 1, and plus iota, the value of sine of 0 is equals to 0. So here we just get that e to the power of iota 0 is equals to 1. So it means that the value of Euler's identity for theta equals to 0 is equals to 1. So that now we take the general Euler's identity here, and we take the general value is e to the power of 2k pi iota is equals to cos of 2k pi plus iota sine of 2k pi. So here the value of k is equals to 1, 2, 3 and up to so on. So in order to further solve this problem, we here we just write an important fact about the even and odd multiples of cos and sine inside its angle. So here we know that if you have cos of even multiple of theta, so it is equals to always equals to plus 1. And if you have a sine of even multiple of theta, it always gives us the even multiple of pi. Sorry, this is even multiple of pi. So this is always gives us the value 0. Similarly, for odd case, we have the cos of odd multiple of pi is equals to minus 1, and sine of odd multiple of pi is always gives us the value is 0. So here we use these values for further solve the above equation. And now in the next step here, first we copy down the Euler's identity here. It is 2k pi iota equals to cos of 2k pi plus iota sine of 2k pi. Here we first check the behavior of this Euler's identity for the value of k equals to 1. So when we take k equals to 1, our above equation is written as e to the power of 2 pi iota is equals to cos of 2 pi plus iota sine of 2 pi. Okay, so here we know about the above fact which we just stated here. According to this fact, we have even multiple of pi becomes 1. So you see that this is cos of even multiple of pi. The output of this is 1, and plus iota, this is the even multiple of pi, it is equals to 0. So it means that the value of e to the power of 2 pi iota is equals to 1. So that now it means that for k equals to 1, our Euler's identity is equals to 1. Now we check at k equals to 2. So when you check k equals to 2, it means that we put this k equals to 2 here and we check its behavior. So we get e to the power of 4 pi iota is equals to cos of 4 pi plus iota sine of 4 pi. And now in the next step, we see here this is also a cos of even multiple of pi, it is equals to minus 1 plus iota, this is even multiple of pi, it is equals to 0. So here we have this is e to the power of 4 pi iota is equals to, so this is also plus 1, it is equals to plus 1. And now we check the behavior of above Euler's identity for k equals to 3. So when you take k equals to 3, our above equation is written as e to the power of 6 pi iota is equals to cos of 6 pi plus iota sine of 6 pi. And now in the next step, we have the value of cos of 6 pi is equals to plus 1 and the value of sine 6 pi equals to 0. So we have e to the power of 6 pi iota is equals to 1. So from these values of k, here we just conclude that our above Euler's identity is equals to 1. We just write it here, e to the power of 2k pi iota is equals to 1 for k equals to 1, 2, 3, 4 and up to so on. So that here we solve this problem for the values of n. Now we take nth power on both of the sides and it is written as e to the power of 2k pi iota and its whole power n equals to 1 to the power of n. And now in the start of the problem, we have the value of 1 to the power of n equals to minus 4. So that now we use this value of 1 to the power of n here. So when you substitute 1 to the power of n equals to minus 4, so this expression, this equation is implies that here we multiply these two exponents and it is written as e to the power of 2k pi n iota equals to minus 4. So because we solve this problem for the values of n, here we need to take the log on both of the sides. So when so that when we take this natural log, it is written as e to the power of 2k pi n iota equals to log of minus 4. So now in the next step here we use the nice property of log and we move this exponent in the front of this log and it is written as 2k pi n iota into log of e is equals to log of minus 4. And here we know that the value of this log e is equals to 1. It means that here we have 2k pi n iota is equals to log of minus 4. And now because we find the value of n, so that we move all the other terms to the right hand side and you finally get the value of n equals to log of minus 4 divided by 2k pi iota. So this is the complex roots of the given equation for our k is equals to 1, 2, 3 and up to so on. So this is the final answer of this question and thank you so much for watching this video. Please subscribe to my channel for more exciting videos.